Ever feel like, whoa, my phone can do more than like those giant computers from the movies?
You're not wrong. It's pretty wild when you think about it.
So we're going deep on computer architecture today, right? Like not just the code, but the actual systems behind it all.
Yeah. The stuff that makes all that tech stuff actually tick, we're going all the way back to the start, too.
Cool. Because I've always wondered, like, when did we go from those room-sized things to, like, AI in my pocket?
It's a journey, for sure. Imagine back in the 50s, it was all vacuum tubes and punch cards.
Oh, I've seen pictures. Crazy, right?
Giant machines like EDSAC, basically just glorified calculators, each instruction, one step at a time.
So when did things speed up?
Transistors. That was the first big leap. Shrunk those behemoths onto a chip.
Okay, so smaller, but when did it really take off? Was that Moore's Law kicking in?
Exactly. Moore's law basically predicted how many transistors you could fit on a chip would double every 2 years, like exponential growth.
And that's why tech just exploded, right?
Totally. More power, smaller size, cheaper. That's how we got from clunky computers to what we have now.
It's kind of mind-blowing, honestly. But, like, even Moore's Law has a limit, right? What happens when we hit that wall?
That's the big question everyone wants to know. We're already pushing those physical limits.
How do you mean?
Well, you can only shrink a transistor so far. And heat, that's a huge E problem. Too much power in a tiny space, things melt.
Yikes. Okay, so what's the plan? Are we stuck?
No, not stuck. There are some brilliant minds working on this. One idea is 3D chip stacking. Instead of going smaller, build upwards.
Oh, like a skyscraper of chips.
Kind of. And then there's the really wild card, quantum computing. That could change everything. But we'll get to that later.
Okay, got to keep us in suspense.
Yeah.
So, computer architecture is designing all these systems, but what's the point? What can we do with it?
Think of anything a computer does. Browsing the web, streaming, turning on. Architecture makes it happen. And it's not just speed, though that's part of it.
Right, because my phone's fast, but it's more than that.
It's got to be efficient. Use power wisely, be affordable, and just, run smoothly.
So it's like beyond fast, it's got to be smart.
Exactly. Like your phone's battery lasts all day. That's good architecture. Or those giant data centers for the cloud. They use a ton of power.
So there's a huge cost and environmental impact too.
Huge. Making them efficient is important for everyone.
Yeah, that makes sense. But this all sounds crazy complicated. Are there, like, different types of computer architecture?
Absolutely. You've got microarchitecture. That's the nitty-gritty, how the processor works at the circuit level. Imagine designing a car engine.
Oh, wow. So that level of detail?
Yep, making sure it's powerful and efficient.
Okay, so microarchitecture, like the engine room. What else?
Then there's instruction set architecture. That's like the language programmers use to talk to the hardware. Think of it as the car's dashboard.
The controls, making it easy to use.
Right. And then you've got system architecture, the big picture. How does the processor, memory, everything all talk to each other? So the whole car, how it handles.
Okay, so depending on what you're building a phone, a giant server, you focus on different things.
Of course. Different needs, right? A phone needs to be energy efficient. A server needs to handle tons of data super fast.
It's about matching the design to what it actually needs to do.
Exactly.
So what's next? What's cutting edge in computer architecture these days?
The big thing now is parallelism. Instead of making one processor crazy fast, which is getting harder, we're putting multiple cores on a single chip.
More cores, more power.
Basically, and that's where GPUs come in. They were for graphics, but now they're used for anything that needs massive parallel processing, like AI.
So GPUs aren't just for gamers anymore. That's so cool. Can you give us a real-world example of how this works, like on the chip itself?
Sure, think about the memory hierarchy inside your computer. You've got different levels of cache, L1, L2, sometimes L3.
Cache, like where things are stored?
Yeah, so L1 is super fast, like your brain's short-term memory. L2 is a bit slower for things you use less often.
So it's about organizing information for quick access,
Exactly. Minimize the time the processor is waiting for data.
which slows everything down if it's not organized.
Big time bottleneck. But faster memory is more expensive, so it's a balancing act.
Like anything else, got to pay for the good stuff. But with all this progress, what are the challenges?
Well, besides Moore's law ending and heat, there's more. Building at the nanometer scale is really hard, really expensive.
So it's a constant push to go smaller, be more efficient.
Absolutely. And don't forget, hardware is only half the story.
Oh, right. The software needs to keep up.
Exactly. If the software isn't designed to use the new hardware well, it's not much use. It's a team effort.
Makes sense. So We've been talking about computer architecture, but how's that different from computer science? They seem related.
They are, but computer science is more about algorithms, the software, the theory. It's like composing music,
Oh, I like that. And computer architecture is?
building the instruments, making the hardware that can actually play that music.
Ah, I love that. So you need both to make it work.
You got it. You know, it's funny. The music analogy always makes me think of what we do. It's like trying to get the hardware and software to harmonize, you know?
Right. Like they need to be in sync or the whole thing falls apart. And speaking of things that can fall apart, you mentioned those big data centers. They need to be energy efficient. Why is that such a big deal?
Well, just picture it. A giant warehouse full of servers running all the time, all over the world. It's a huge amount of energy, not to mention all that heat.
Oh, right, because those servers get hot.
Super hot. So you have to cool them down, which uses even more energy. It's expensive and it's bad for the environment.
Okay, yeah, that's a double whammy. So computer architecture can help make them more efficient.
It's a big part of it. By optimizing the design, we can reduce energy consumption. For example, more efficient processors, smarter memory, even the layout of the components on a chip.
Wow, so even tiny things make a difference.
It all adds up. And it's constantly evolving, finding new ways to be more efficient as technology gets more powerful.
It's like a constant race to stay ahead. You mentioned quantum computing earlier, and that could be a big deal. What exactly is that?
Okay, so imagine a computer that can be in multiple states at the same time.
Okay, that sounds kind of impossible.
That's quantum computing. It uses qubits instead of bits. A bit is a 0 or a 1. A qubit can be both at the same time. It's like superposition.
That's wild. So how does it make it so much more powerful?
Think of it like this. It could solve problems that would take a regular computer billions of years in, like a day. Things like breaking encryption, simulating molecules for medicine, even designing new materials.
Okay, now that's a game changer. But you said it's still early days.
Very early. We're still figuring out how to control these qubits, how to program them, how to build the hardware. It's a huge challenge.
But it sounds worth it with that kind of potential. So how would quantum computing change computer architecture?
Well, that's the big unknown. Quantum computers are so different from what we have now, we might have to rethink everything. Processors, memory, the whole thing.
So the future of computers might be completely different from what we're used to.
It's definitely possible. But that's what's exciting about it, right? Always pushing boundaries, seeing what's possible.
I love that. Okay, but let's come back to the present for a minute. We talked about data centers. What about our phones and laptops? How is architecture tackling energy efficiency there?
Good point. Mobile devices have their own challenges. They have to be powerful, but also last a long time on battery.
Because no one wants a phone that dies in 2 hours.
Exactly. We need those phones to last all day. So designers are trying to get the most performance with the least amount of power.
How do they do that? What are they actually working on?
Well, take ARM architecture. It's designed for low-power devices, like phones. It prioritizes efficiency over raw power.
So it's about using the right tool for the job, right?
Yes, you don't need a giant truck to carry a loaf of bread. ARM is like that efficient car, perfect for everyday tasks.
Okay, that makes sense. So it's not always about bigger and faster, but also smarter and more efficient.
Exactly. And that's what's so great about computer architecture. It's about finding the balance. Whether it's a supercomputer or a smartwatch, it's about making it the best it can be for what it needs to do.
It's really amazing how much computer architecture affects everything, even if we don't realize it.
It's everywhere, right? And it just keeps changing, always pushing for more power, more efficiency, always something new.
And with quantum computing coming, who knows what's next? Seems like computer architects are going to be busy.
Oh, absolutely. They're like
Yeah.
the architects of the whole digital world. What they do shapes all this technology we rely on.
So true. Well, this has been an incredible journey from those giant old computers to, well, whatever comes next. Any final thoughts?
I think next time you use your phone or laptop or see something amazing tech-wise, just take a second. Think about the hardware and software working together.
It really is incredible when you think about it.
Yeah, it's human ingenuity at its finest. And the future. Who knows what's possible?
That's what I love about it. Well, thanks for taking this deep dive with us. It's been awesome.
My pleasure. Anytime.